So you're all familiar with group sequential designs when you have two arms. Okay, this is just a generalization of that, and it's an alternative to the combination function approach of the group from Austria and Germany that has been very busy on this end, Posserol and Frank Bretz and all these guys. So in the current implementation that we have in East is that we might have, as I said, many arms, and we might have different stages. We can stop the trial if the efficacy boundary is crossed by any of the three arms, or we can stop the trial if the futility boundary is crossed by all arms. Okay? If the futility boundary is not crossed by all arms, by some of the arms, these arms will just be dropped for the next stage. Okay? So then we'll continue to the next stage with only the winners, the ones that made it up to that point. Okay? And as you will see in the software, in its simulation mode, we can do dose selection, and also we can do adaptive sample size re-estimation with this approach, using the promising zone approach. So that means that if you unblind the data up to that point, you see what your observed treatment effect was, you can actually adjust upwards the sample size by comparing either the conditional power to see whether the conditional power falls within a couple of thresholds, or whether the observed test statistic falls within these thresholds. Again, this is an extension of the sample size re-estimation procedures that we have for two arms. Mathematically, it's not such a big change. When we have just two arms, what we want to do is we want to control type 1 error in this sense. We're looking at the walled statistic, and we want the probability that we remain within the bounds under the null hypothesis to be alpha. And remaining within the bounds means that we do not cross the upper bound and we do not cross the lower bound as well. When you have multiple arms, instead of looking at just one single upper bound and one single lower bound, you look at the maximum of the upper bounds and you look at the maximum of the lower bounds. And you want to find the chance that you do not cross the maximum of these, and you want to maintain the probability that that happens under the null hypothesis to be alpha. So this is actually a generalization of Dunnett's test. So in a two-arm trial, this is what happens. Each one of these walled statistics are scalars. These are the boundaries that you have. So if at look 1 you do not cross the boundary, at look 2 you do not cross the boundary, and then at look 3 you cross the boundary, then you would stop the trial. While and you want, under the null hypothesis, the probability of this happening to be alpha, right? While in the multi-arm stage, these W's are not scalars, but they are vectors now. And now the trial will stop if the maximum of the components of the vector at the first stage is above the threshold, or the maximum of the components of the vector at the second stage is above the threshold, or the maximum of the components at the third stage is above the threshold. So the computations here are more complex because in the two-arm stage, the property that drives this procedure is the independent increment process property, right? While here, you have that the components within each one of these vectors are going to be correlated. The increments are still going to be independent. So the vectors themselves from one step, and then the increment of that vector will be independent, but you will still have correlation within these components. So that makes things more complicated. So, yeah.
Can you set this up so that, say, you only do futility stopping at certain analyses so that you'd have like an infinity boundary or something?
Yes, you can. Right, you can do it. Right. Right. So you will actually see it. So actually, the futility boundary is the one that takes the bigger time to calculate. So yeah, if you don't have that, obviously, yeah, it's going to be easier. So here we have 3 doses compared to placebo. The endpoint is week 2 change from baseline in 24-hour trough FEV1. And what we do is we expect differences from placebo between 14 and 18% with a standard deviation of 0.5. So we want to design this with 90% power for a one-sided alpha of 0.025. Okay, so we have these 3 dose levels. How you would do this if you only wanted to utilize the machinery that you have for group sequential designs with 2 parallel arms, right? So the way that you would do it is that you would take, let me just go here in, oh, I have closed this. Let me open it up again. So I would go into the many samples. Well, initially I would just go to 2 samples, right? In 2 samples, and I would look at the difference of means. And if I want the difference of means with how many looks we have here, oops. So here we have 3 looks and 90% power and 0.025. And we want that difference to be 3 looks, 90% power, and we're looking at the difference of means of 0.18 with a standard deviation of, what does the standard deviation look like? 0.5. Okay, so if I go here, the standard deviation of 0.5. And if so this will be a fixed sample size design as it is right now. If I wanted to convert this into a group sequential design, then I would have to change the number of looks to 3, have 2 interim looks and 1 final analysis. And then, for the moment, if I wanted to just use an efficacy stopping rule, I could use any one of the spending functions. So if I use the Lan and the Metz family of spending functions, I can select either the O'Brien and Fleming type or the Pocock type. So in our example here, we used the O'Brien and Fleming type for efficacy, and we didn't use any futility boundaries. I didn't use any futility here. So for the moment, let me just leave it at this. So these are the efficacy boundaries that I'm looking at. Okay, one-sided efficacy boundaries. And if I try and compute the design to see how many subjects I would need, and I enter this into my workbook, we will see that I will need 165 subjects per arm. That's the maximum sample size. Or if the treatment works, for this difference, target difference of 18%, I would need, on average, 132 subjects per arm, okay? Or a total of 264 subjects altogether. So naively, if you were to deal with this problem naively and say instead of having 3 arms versus placebo, but we just want to explore what happens when we have the machinery for 2 arms, you would say, okay, I would need for a 0.025 alpha and 90% power these number of subjects. So if I wanted to expand in what would happen with 4 arms, 3 control versus placebo, well, then all I have to do is I would probably just need to divide this by 3. And instead of having 0.025, have 0.025 by 3 in here. Just go here in the alpha and just make this 0.025 divided by 3, which is 0.008. And then just compute what the sample size would be for that alpha. So you're essentially making a crude Bonferroni adjustment. And you can see that with a crude Bonferroni adjustment, you would need 210 subjects per arm. So if you were to extrapolate to 4 arms, you would just have to multiply this by 4. Okay? And you would have 840 subjects. And that would be the naive way of doing things. Okay? But for just a 2-arm study with a 0.025 alpha and 90%, you need, as you see here, as we actually saw on the output of yeast itself, 132 subjects per arm on average, if the drug works. Okay? But what we want to do is we actually want to do simultaneous inference. So instead of just looking at 2 arms at a time, I want to be able to assume that, for example, what happens if all the differences that I'm targeting between the 4 treatments are in the order of 18% with a standard deviation of 0.5, and what the resulting sample is going to be. So per arm, the maximum is around 130 subjects for this. Or the expected value per arm is going to be 104. So it drops quite significantly there. Remember, before we had the average was 132 per arm. Now the maximum sample size is 130 per arm for the same type of difference. Okay? And the way that you would be able to run this into EAST is by you would go into the many samples now. You would select multiple looks, combining p-values, the MAMS approach. Multiple arms, multiple stages, this approach, the group sequential. Click on OK, and then we still have 0.025, 90% power. The common standard deviation is 0.5 all the way through. And we would have 4 arms, and we have 3 looks. Okay? So for the 4 arms, we want to make the mean 0.18 all the way through. The difference from the mean, 0.18. The standard deviation is 0.5. And in terms of the boundaries, again, I'm going to be exploring O'Brien and Fleming type of boundaries, okay, with this. So if I click on compute here, then I should be getting exactly what I ended up having on the output. So if I look at it on the detailed view, you can see now that we have 130 subjects per arm, and on average 104 subjects. Okay, so actually I have run many more cases here, so let me just open my workbook so that something that I have already saved in here so that I don't have to run these from the beginning. So it has the enhance study, and the one that we just saw here is this one, the 4-arm study that I just run. Okay, now the number of subjects that we have is smaller. The boundaries, however, if you look at the boundaries of the detailed look for the z-scale, they have changed. So for the 2-arm case, in order to be able to stop at any interim look, you have to stop to a boundary that is 3.7 at the first look, 2.5 at the second look, and the final look is 1.9. While the boundaries are higher on the multi-arm design. Instead of 3.7, it's almost 4. Instead of 2.5, it's 2.8. And instead of 1.9, it's close to 2.4. Well, why is that? Right, so this is the comparison of the boundaries at each arm. So you can see that they are higher for the multi-arm case. And they are higher because you have a higher chance of crossing the boundaries under the null hypothesis with the 4-arm trial, because you might cross them for different components of each one of the 4 arms crossing that boundary. So you have more chances to exit under the alternative hypothesis. So in comparing the two, this is what you would see there. Now, what you may also want to see is what happens if now you do not have the same value of delta for each treatment, right? Before we had for the 2-arm that the anticipated difference, the target difference was 0.18. We tried to see what would happen in the corresponding case for the 4 arms, with the difference being 0.18. What would happen if, say, for the 2 of the arms, the difference was 0.14 instead of 0.18 over there? Okay, so again, I have tried this over here. So this is the second scenario that I run. And what you get to see is now that the sample size is going to be higher because we're targeting smaller differences for some of the components. So it's 168 per arm, 135 are the expected sample sizes. So we have that the 4-arm design will require more subjects than the 2-arm design. And this higher efficacy boundary hurdle is not going to be offset by the extra opportunities to cross the efficacy boundary, because only one of the doses will have a strong effect. Only one of the doses we're targeting an effect in the order of 0.18. So then the next step would be, well, what happens if we now include a futility boundary in there? All right. So this step, actually, if you were to run it for this scenario, the scenario of the difference of 0.18, 0.14, and 0.14, this is the one that takes roughly about 4 to 5 minutes to calculate the futility boundaries, because this is an iterative process. And these 4 to 5 minutes are actually an improvement over what is currently out there in the literature. So this is a problem that has been tackled by researchers at the MRC as well. And I'm just going to be going a little bit further down the line just to give you what they have reported. Okay, so this is a published paper by Statistics in Medicine by Jackie et al., Wyson and Jackie. This was for a 4-arm 4-look design. And this was on a pretty powerful machine, not my laptop here. So with 2 arms and 4 stages, it's very manageable. If they were to do it with 4 arms and 4 stages, it would take 8.2 hours to get the boundaries, the futility boundaries. And this also speaks for the sort of like great team of computer programmers that we have in India, which with the optimization procedures that we're undertaking, that we have managed to put it to under 4 minutes in this particular situation. So if you were to add the futility arm, so I'm going to edit this design so that you can see it, because I'm not going to run it, because we'll have to wait 4 minutes for this to run, and not going to wait for that. So here, you can select, even within futility, different spending functions, gamma spending functions, Lana and Demet spending functions, and within that, I selected O'Brien and Fleming, which is what was run in there. And these are what the boundaries look like. And this is the part that if you make any change here, say, for example, from Lana and Demet make a gamma family change, and I ask it, once it's done, to recalculate the boundaries, this part alone will take 4 minutes. So this is something that we don't want to try. So, but once you have the boundaries set, and once you know what the futility boundaries is, what you can do is you can actually experiment through simulation and see what would happen if you change the sample sizes for those boundaries, and what achieved power you would have for those sample sizes. So once you have the design, you can click on the simulation icon, which allows you to simulate from a particular design. Okay? And for this particular example that we had here, by introducing the futility rule, we saw that we would need 671 subjects in order to be able to have 90% power, okay, with these particular boundaries, Lana and Demet's for efficacy and for futility, and this particular truth about the targeted differences from the mean, 0.18, 0.14, and 0.14. So this I can actually now simulate, okay, and see what my achieved power will be. So since I designed this trial for 90% power, if I were to repeat these simulations 10,000 times, and you can see how the simulations are running, then I should be expecting to reject the null hypothesis 90% of the time. So if I enter these simulation results into my workbook and I look at them here, then you can see that indeed what I'm having in those 10,000 simulations, I ended up with a global power of 88.22 27%, right? So out of the 10,000 simulations, I rejected the null hypothesis 8,800 times, 8,827 times. But with this, you're also getting much more information, because first of all, you're getting information on how often you ended up stopping at each one of the different stages for efficacy and for futility. So you can see here, we ended up in 366 of the cases stopping for efficacy at the first look, and in 56 of the cases we stopped for futility at the first look. Okay, but these numbers were expected because you would get these probabilities on the design table as well. But what is also interesting here is you see in these simulations how often you ended up dropping an arm at look 1, at look 2, etc. So at interim 1, look 1, you ended up continuing with 3 arms 95% of the time. An interim look 2, you ended up continuing with 3 arms 37% of the time. Okay? And the arms that ended up being moved into the next stage can be seen here. So this is the marginal probability of trial termination by treatment at each look. So you can see with respect to treatment 1, this is the treatment that had, we were targeting 18% difference of it. So we ended up with treatment 1 winning 71% of the time overall, 2.5% at the first look, 42% at the second look, and 26% at the third look. While with treatment 2, remember that was one of the 2 treatments that had a 14% target difference, we ended up winning half of that, 37% of the time, and same thing with treatment 3, also 38%. 39% of the time. And you can also see in how many cases we ended up stopping for futility and for efficacy with any one of these situations. And then you have all the detailed efficacy outcomes. In how many cases you ended up only with treatment 1 winning, with treatment 2 and treatment 3 alone, and then with combinations of 1 and 2, and with all 3 treatments alone, which did not happen that often. Okay, so there is quite a bit of extensive details that you would get through a simulation when you're running a simulation. Let me go back to the simulation input window because I wanted to show you one more thing here. So there's 2 buttons here. Because of the real estate, you're not able to see the second button. So the first one here is the treatment select button. So this allows you, so this is one of the functionalities that I mentioned before. It will bring up a new tab in your simulation, which is called the treatment selection tab. Once you select that, then you can actually tell the software to, at each stage, to move ahead with either the best or the best 2 or the best 3 treatments and so forth like this. And then you can combine the results. So you can make the treatment effect scale either in the wall statistic scale or in different other scales in terms of effect size, isotonic mean, etc. And for example, if you only wanted to select the 2 best treatments to move ahead, then you would have the option to reallocate the remaining sample size to the arm that was from the arm that the treatment arms that were dropped into the remaining arms. Window, yeah, in your case it is. You see, there is this button which is called the SSR button, which I think, as I said, my version, I just installed it on Friday. So I think they're probably doing a little bit more work on it. So this SSR button allows you to set the stage for the sample size re-estimation, which is, you're checking if your test statistic, say at look 1, falls within different boundaries and a higher and a low threshold, or if equivalently the conditional power falls between these 2 boundaries, then you can increase your sample size up to an increment of the original sample size. But for some reason, this has been just removed in this version, so I think they're testing it. So we have sort of like continuous looks. The version that you have access to on your machines has this SSR button. The version that I just installed on Friday doesn't have it. So, but this is, as I said, this is one of the features that we are continuously working and trying to have it finalized for this next version of it. So probably it has been taken out temporarily from the software. So yeah, so this is what is still being tested, and that's why it has been moved around. So the boundaries, recompute the boundaries if arms are dropped. So essentially taking into account of the spending function, functionality of the bounds that you are using. Make a dose selection at the interim look, which is the current option that I do have available in my machine, and you do have all in yours, the treatment select. And this is the version that you have available, but I don't have, which is to increase the sample size in the promising zone under interim look. And then once you do that, you can actually go head to head and compare the results with the current method that is actually right now the most prominent one. But what we're claiming is that this is actually more effective. But we have put that method available as well into EAST. So this is the methodology of what is called, is usually referred to as the seamless phase 2, phase 3 design. So it's the multiple looks combining p-values design, where if you select it, oops, I didn't select it, multiple looks combining of p-values. Right, so this is, again, you can have, it's typically a 2-look design. So you have at the interim look, before the interim look, you might have a number of arms compared to control. And then at the interim look, you want to select either the best working arm or the 2 best working arms to move into the next phase to be compared against the control. So the way that you would, again, the boundaries, the efficacy boundaries can be in terms of an adjusted p-value. And then the treatment selection, you can select either the best treatment to move into the next stage or select the best 2 treatments to move into the next stage. And then when you have done that, you will be combining the results of the 2 phases with a combination function. So typically, you can use the inverse normal combination of p-values between the 2 stages to do this. And you can also use different multiplicity adjustments for the multiple arms that you have on the first stage, whether this is Bonferroni, the CDAC, SIMS, or the Dunnett parametric test. So this is the method that is currently being used for these phase 2, phase 3 designs, where you have a number of arms in the first stage and you just want to move on to the second stage with a selection of them. But we are also offering this MAMS approach, which I mentioned before, which is a more general approach. Is sort of like a direct generalization of the group sequential designs, where you can do treatment selection if you want, but you can also have this natural way of dropping arms due to failing a futility testing. The other difference between these two is that the post-roll approach, the phase 2, phase 3 approach, is entirely simulation-based. Right? So we opened up this window of the phase 2, phase 3 design, but as you can see, this is actually a simulation window. So this can only be examined through simulation. There's no close-formed expressions that can be that will provide the solution to the problem. While with the MAMS approach, we are doing this first from a design point of view. We're calculating the boundaries. We're able to calculate the chance of crossing the boundaries. And then we're also able to simulate And then within the simulation, you can do the treatment selection as you would do with the phase 2, phase 3 types of designs. And this is pretty much it in terms of the methodology that I wanted to mention for the new advancement in the confirmatory trials that we have been offering. And again, I would be more than happy to illustrate more details